Hi guys, Dr. Tim Kruse, Elementary Statistics, and in this video I'm going to demonstrate how to find confidence intervals for the difference between two proportions. Alright, think of a proportion as a fraction, so you got two groups, and a certain fraction of people in the first group did something, and a certain fraction of people in the second group did something. And we're going to compare those two fractions, or those two proportions. We're going to find the difference between proportion 1 and proportion 2. We're going to examine the difference between those two proportions and create a confidence interval for the difference between those two proportions. All right, a little terminology, and in a previous video, if you want a more in-depth explanation of all these symbols, you might look at a previous video I made that's find confidence intervals for a proportion, for a single proportion. And I'm kind of going to, since I've made that video, I'm going to go over this a little quickly. All right. We're looking for the difference between two proportions. Now, P, when it doesn't have this hat over it, P stands for the true proportion. And that's talking about all people everywhere in the world, or whatever you're measuring. So the true proportion of all these people, all right, maybe that's one ethnicity or something. And this is the true proportion of all this other group of people. Maybe that's a different ethnicity or something. And we want to know if this fraction and this fraction differ. Subtract means differ. Differ means difference. I want to know if these two proportions, these two fractions differ enough so that it's significant, so that they differ so much that it's important, that people care. All right? Or if they're so close together that there's really no difference. That's what we're testing. Our basic formula is P hat for group 1 minus P hat for group 2. Now P hat just stands for my sample, all right? We'll never be able to measure all the people in this group in the whole world. So what we do is we grab a sample of people and we measure that group. And we look for that fraction, that proportion in group 1, and that proportion or fraction in group 2. And we call that P hat, our sample proportion, our sample fraction. So our sample is our best guess at what the true proportion difference would be. All right, we don't know. We'll never know what these numbers are. It's too hard to measure. We can't measure all the people in the world for these groups, for whatever we're measuring. So what we do is we make our best guess. We grab a couple samples, we see how different they are, and we say, well, we think that this number right here, we think that's what the true proportion difference is, give or take a little bit of error. So we can add a little bit of error here and subtract a little bit of error here. Margin of error. I have a hard time saying that. Think about it as a point spread. We're giving ourselves a little extra spread on the right, and we're taking away a little spread on the left. So we're giving ourselves a little give or take. All right, this is our best guess. This P hat 1 minus P hat 2. That's our best guess at what the true proportion difference is. Give a little bit of error and take a little bit of error. All right, now the more specific formula is the difference between our sample proportions minus the z number that fences in our confidence level, and then the rest of it's right here. Your P hat 1 we talked about, that's in group 1, your proportion of people who did what you're measuring. Let's call them successes. Q hat 1 would be the proportion in that same group who did not do what you're measuring. I like to explain it in terms of, chance of rain. If there's a 70% chance it will rain, then there's a 30% chance it will not rain. So Q is the complement of P. This is the chance that it'll happen. This is the chance it won't happen. And N, of course, stands for how many in group 1. Same things on the right here, except for group 2. All right, proportion of people in group 2 who did, proportion of people in group 2 who did not, and over the number in group 2. And the only difference between the left side and the right side is this one's minus and this one's plus. Now we're going to need to interpret our results. When we end up with results, they're either both going to be negative or both going to be positive, or there might be a mixture of positive and negative numbers. And those mean three different conclusions, three different results. So if your results are both negative, if you say the difference between these two proportions is between two negative numbers, Well, if that happens, we can say the group 1 proportion, the group 1 fraction, the fraction of people in group 1 who did this thing is definitely lower than the people in group 2 who did this thing, the proportion in group 2. Significantly is the word we're looking for. So we can say, yes, we are certain that the proportion of people who did this thing in group 1 is significantly less than or lower than or smaller than the proportion of people or the fraction of people in group 2 who did this thing. If both numbers wind up being positive, we turn it around and we say group 1 is bigger than group 2. The proportion of people who did this thing in group 1 is significantly more than the proportion of people who did that thing in group 2. And then if we have a mixture, we're just saying that the numbers are so close together that we really can't be sure. If there's a mixture, it's like we can't call it. It's too close to call. And we say there's no significant difference. Even though maybe one of those may look smaller than the other, they're so close together that we can't really call it as this one's bigger or that one's bigger. They're so close together that it could go either way. All right, it'll make more sense if we work a couple of problems here. So when a group of people was asked, are you a registered voter? Well, some of them don't answer accurately. Some of them, maybe lie or accidentally don't tell the truth, or maybe they just don't like telling people, their business. So out of a sample of 93 people, this is going to be our first group, 79 of them gave the actual accurate answer, which means some of them lied to the person asking the question. And then in another group, another random sample, this group had 83. That's going to be our group 2. Well, 74 out of the 83 answered accurately. We want to find a 95% confidence interval for the difference between the fraction of people who answered accurately in group 1 and the fraction of people who answered accurately in group 2. Organize your information. How many were in group 1? So N1 is 93. Now, what's the true proportion of people who answer accurately and these type of people? That's unknown because I won't be able to gather up all of those people in whatever this group is. All the people in the world, I don't have the time to gather those up, but I can gather up 93 and get an answer from them. So this is our sample, p hat. Nobody knows the true proportion of all the people in the world, but I do know the proportion out of 93. I caught 93 people. I asked them. 79 of them gave me an accurate answer. So you can use either the fraction 79 out of 93 in your calculations, or you can change it to a decimal. Now, the more decimal places you use, the better. Some people will say, as long as you use 4 decimal places, you'll be fine. So 0.8495 is fine most of the time. If you can't get your final answer to match up, go back and use a more exact version of that symbol. All right, but for most cases, 0.8495 would be fine and would get you the right answer every time. All right, Q hat. This, this is still group 1. This is the people who did not answer accurately. So that's the rest of the 93. You can do 93 minus 79 to get this 14 out of 93 if you like. 14 out of 93 gives you this decimal over here. Probably a quicker way of getting that same decimal is just doing 1 minus this guy, all right? 1 minus the people who answered accurately, because these are going to add up to 100%, or they're going to add up to 1 if you're speaking decimal. If, let's call that 85%, if 85% answered accurately, that means that 15% did not answer accurately. To get 15%, you can do 100% minus 85%. So we're doing the same thing with decimals. If you figure out what p hat is as a decimal, and then you want to find the rest of it, just subtract that from 1. Excuse me. All right, over in group 2, we had 74 out of 83 answered accurately as a decimal. It looks like this. You're probably fine if you use 4 numbers after the decimal, 8, 9, 1, 6. That's going to round it up. If you can't get the right answer, or you can't get your answer to match up to the book answer, then just come back and use a more accurate version of p hat. Q hat 2 is the rest of them. So like I said, you can just subtract this, subtract it from 1, and that's going to get you this decimal over here. You're also welcome to use this fraction, all right? It's whatever you feel more comfortable with. Most calculations I've seen, they tell you to use the decimal and just round it to 4 decimal places. But the fraction, if you use it, it's actually perfect. This is exact, whereas over here we're rounding, so it's less exact. But as long as you go 4 decimal places, 1084, your calculations should be fine. All right, so we want a 95% confidence interval. That means I need a fence here on the left and a fence here on the right, and I need that to fence in 95% of the area of the curve. And we need to look up this number and this number, these z numbers that fence in 95% of the curve. I have them written here, but that's something you have to look up. You're wondering what z numbers will fence in 95% of the curve, and I'll show you a couple of ways to do that. The first way is just to figure out what's in this left tail here and look that up in your z table. So think about it. If there's 95% in the middle, that means there's 5% left over, and we have to split half of it here in the left tail and half of it in the right tail. So that's 2.5% left and 2.5% right, because it has to add up to 100%. All right, if this is 2.5%, that means the decimal is 0.025. I want to look up a z number that has an area of 0.025. So I grab my z table here, and I'm looking for, these are areas right here. This is area under the curve, and I'm looking for 0.025. There it is right there. So now just figure out what z number produced this area. That's negative 1.9 and go up to 6. That's not too bad. So first method is, sorry, I'm shaking everything. First method is figure out how much area is in this left tail and then look up the z number that produced that area. So we said 95%, that leaves 5%, so 2.5% here, 2.5% here. I'm going to look up 2.5%. That's 0.025. And I look and I look and I look and I find out that this z number produced 0.025. And then since 95% is dead center, right smack in the middle, that means the right side is the same number but positive. All right, a second way to find that number, a little easier, is most z tables will have those confidence intervals figured out for you here on the left, bottom left. If not, just copy this down, but they've already figured these out. 95% confidence interval means from negative 1.96 to positive 1.96. And maybe an 80% confidence level would be between the 1.28s, from negative 1.28 to positive 1.28, and so on. All right, and then a nice quick way to get this number. I mean, you don't need a z table. Everything's in your calculator. But let's look this up on the calculator instead. So remember, there's 2.5% area in the left tail here. That's 0.025. And I want to look up the z number that produced 0.025. Well, I'm going to tell the calculator to do it. I'm going to I'm going to push distribution here. So second distribution. And now I want to do number 3. That's an inverse normal. All right. This is a picture of a normal distribution curve, and normally we give it the z number and it tells us the area. So normally I would say, okay, negative 1.96, what's the area? And they would tell me 0.0250. But I'm going to go backwards. That's what inverse means. So I'm going to go backwards. I'm going to give it the area, 0.025, and I'm going to ask it to tell me what the z number is. So inverse normal, choose it. Now what's the area? The area is 2.5%, so that's 0.025. And then as far as mu being 0 and standard deviation being 1, they're just talking about the marks on your curve here. The middle's mu, that's 0. 1, 2, 3. Since we're going by ones, that's my standard deviation. It's going +1, +1, +1. So mu is 0 with a standard deviation of 1. That's just a standard normal curve. And then I just ask it, hit enter one time, and I ask it, go find that z that gives me 2.5% to the left. And it finds a really exact representation of that negative 1.96. All right, so back to our problem. I know that the difference between the two proportions is between the 1.96s if I'm speaking z, if I'm using z-scores. But I want to use numbers from my word problem from, I want to call them X, and they need to relate to the problem. So I need to change these 1.96s to storybook problems, all right, my word problem numbers. So I want to say the difference of the proportions is between, and then I want these two numbers to come from the problem. All right, here's our formula. Let me, I can't quite see it all. There we go, let's try that. All right, so I'm going to say the difference between the proportions is between what I think the difference is, this is my best guess, minus a little bit of error, and what I think the proportion is, this is my best guess, plus a little bit of error, plus a little bit of point spread. So give or take some point spread. All right, we call it margin of error. Here's a more specific formula, and here's the substitution. So p hat 1.8495. Oops, hang on, we got a glitch. Okay, all better. All right, so we're just substituting those numbers from our information earlier, all right? And notice I just went 4 decimal places, and for me, everything worked out fine. But if you get down to your final answers and they don't quite match up to what you want them to be, then go back and use, the first thing I'd do is I would use a more accurate Z. And if that doesn't work, then I would go back and use a more accurate p hat 1 and a more accurate p hat 2, that kind of thing. First thing I would try though is this Z, or if you're doing something else and it's a T, the first thing I do is I change that to a more accurate representation of this number, and that usually fixes it. But like I said, most of the time 4 decimal places will get you an acceptable answer, so it matches up to your book or whatever. All right, subtract the p hats minus my Z score that fences in my 95%. P hat 1, Q hat 1. This is both group 1, all right, divided by how big the group 1 is. This is both group 2, proportion of success, proportion of failure, divided by how big the group 2 is, 83. Over here, same thing except plus, and we wind up with these two numbers right here. So I'm saying the difference of the true proportion, whatever that is, if I was able to measure all the people in the world, the difference between these two proportions, I'm pretty sure, would lie between these two numbers. How sure am I? I'm 95% sure. I'm using 1.96 because I'm bracketing in a 95% confidence interval. All right, so let's state our conclusion now. Now, we are 95% confident that the interval, see confidence interval, we're 95% confident that the interval between these two numbers contains whatever the true difference of proportions is, all right? If we were able to measure all the people of the world and subtract those two fractions, we're pretty sure it would lie between these two numbers. We're 95% sure it would lie between these two numbers. Now, since the numbers are a mixture of positive and negative, they're not both positive, they're not both negative, well, that just means they're too close to call, all right? I don't know who the winner is. We can't draw a conclusion. So on this one here, I'm going to say, well, one looks smaller than the other, but they're so close together that there is no significant difference between these two. All right, let's do a couple more, and that'll probably cover this. So a random sample of 230 permanent Navajo dwellings showed that 50 of them were traditional Navajo hogans. So we're measuring what proportion of Navajo houses are hogans. All right, so in this first group, they said out of 230, 50 were traditional. So 50 out of 230, that's our first group. That's P hat 1. My sample is 230. 50 out of 230 are going to be P hat 1. Right? Another sample, different group, different area, different state, whatever. They measured 141 houses, and it showed that 19 of those were traditional. So this is group 2. That's going to be P hat 2, 19 out of 141. And find a 95% confidence interval for the difference between the true proportions. Remember, we don't know the true proportions. We only measured 230 and 141. That's not all the Navajo houses in the world. All right, if you were able to somehow measure all the Navajo houses in the world, you'd be able to calculate the difference between the two proportions, but we don't have the time to do that. All we had the time to do was measure 230 houses in group 1 and 141 houses in group 2. All right, so that's where we make our best guess. Let's organize here. Group 1, 230. Group 2, 141. The true proportion is unknown. We'll never know that. We're never going to go find every Navajo house in the world and measure the difference in proportions. What we can do is we can grab 230 houses in group 1 and wherever that area is or wherever that state is. So this is my sample. We mark it with a hat. So P hat 1, 50 out of my 230, that's 0.2174 if you round that 3 up, which means that the ones who were not traditional, well, that's the rest of them, all right? If 50 were, that means 180 were not, for a total of 230. You can just do 230 minus 50 to get 180 if you want to. All right, gives me this decimal here. Or, like I said, another way is once you figure out what P hat is, just subtract it from 1 to get Q hat. Group 2, 141 houses. The true proportion of group 2 is unknown. We'll never know. We're never going to all those houses, but we did go to 141. So the fraction that were Hogan's, 19 out of 141. The proportion that were not, well, that's the rest of them. If 19 were, then 122 were not, for a total of 141. And there's your decimals. Again, 4 decimal places is almost always enough. 0.1348 is usually fine. 95% means that the Z numbers are going to be both of the 1.96s. Here's a more precise 1.96. All right, so it looks like this. The 1.96s are fencing in 95% of the area. All right, so I know the difference of the true proportions is somewhere between the 1.96s if we're speaking this language, if we're speaking Z-score. We don't want to speak Z-score. We want to use the X data. We want to use data from our word problem. I need to know, the difference in traditional Hogan's. So what I need to do is change these 1.96s to story problem numbers. So the difference of the true proportions lies between, and we're looking for those two numbers. Use our formula to convert these two. All right, there's your general formula. It's our best guess plus or minus a bit of error. All right, we don't know what this is. This is our best guess. We're making a guess at what the true proportion is based on our sample. All right, here's the more precise formula, and then we jump to the substitution. So substitution just comes right off your organized information. Notice I went 4 decimal places for all my numbers, and my answer turned out just fine. Usually it does. And I just used 1.96 for my Z numbers, and my answer turned out just fine. But if for some reason your answers don't match what they're supposed to be or what the book says they're supposed to be, first thing I would change is I'd make Z a little more accurate. If that doesn't work, then I would make all the rest of the numbers a little more accurate. But I came up with the difference between the true proportions, which we don't know what that is, all right? But we made our best guess and we said we're pretty sure that the difference lies between these two numbers right here. We're 95% sure of that. So now let's say that in words. All right, we are 95% confident that the interval between these two numbers contains the true difference of proportions. Difference means subtract, all right? Contains the true difference of the proportions. Since the numbers are both positive, that's positive and that's positive, well, then we're 95% confident that the first group proportion, the first fraction, is bigger than the second fraction. And not only bigger, but significantly bigger. We're 95% confident that the proportion of traditional Hogan's in group 1 is not just higher, but significantly higher than the proportion of traditional Hogan's in group 2. If they're both positive, you say, yes, group 1 is definitely a lot bigger than group 2. In this case, we're talking proportions. In this case, we're talking fractions. So the fraction of traditional Hogan's in group 1 is a lot more than the fraction of traditional Hogan's in group 2. Now, for my last example, I got a little lazy and I just did the same problem, but I switched the groups. I had the groups switch places. So group 1 is now the 141 houses in my sample, and group 2 is the 230 houses in my sample. All the proportions I left the same, all right? I switched group 1 and group 2, all right? Let's work it out again with group 1 and group 2 switched. Here's our work, all right? So notice the only thing that switched is basically these two numbers switched places, all right? And then all the group 2 information is now over here, all right? Because this is group 1, this is group 2. So everybody just basically swapped places. What happens when you do that? Well, notice that when you swap these numbers, you wind up with a negative answer, all right? That's kind of interesting. So it's the same information, but I swapped places, and now look what we're saying. We're saying, well, based on this information, I think the difference between the two groups, the difference between the two fractions, is between this negative number and this negative number. Well, now both the numbers are negative. So I'm saying we're 95% confident that the interval between these two negative numbers contains the true difference between the two proportions. Since the numbers are both negative, we're 95% confident that the first group is a lot smaller than the second group. That's the opposite of what we said just before. Since they're both negative, the first group is significantly smaller than the second group. So now we just say that using words from the problem. All right. We are 95% confident that the proportion of traditional Hogans in group 1 is significantly lower than the proportion of traditional Hogans in group 2. All right, so I just flipped the groups. I just had them switch places because I wanted to show you an example where they both wound up negative. And so now group 1 is smaller than group 2. The proportion in group 1 is smaller than the proportion in group 2. All right, guys, that's it.